Okay.
I'll put that in. Hello. Hi. Oh, it's a good turnout, wasn't it? Very nice. Hello. Oh, I have some very familiar faces from year 8 and year 10. I thought after Tuesday it deserved a little talking about. I'm sure that everybody in the room has seen a lightning strike before, and you've seen lightning, heard thunder, been in a storm. However, judging from the number of questions I've had over the past few days, it takes nothing like a life-threatening experience to increase the curiosity around the school, and it's been really good to see everybody asking me loads of questions. So this is dramatically underprepared. I advertised it before I prepared it, but I thought it would be good to get it now while people are still curious. I thought in a few days, as one of my best students there, Jamie, said, that people will just forget, and now's the time to talk about it. It's been really interesting to hear lots of people's accounts of what happened and the things they had to say about it. Some people I've spoken to have had various, you might call alternative theories. I'll give you a couple. So during the storm last Tuesday, I was in a music practice room with Mike. We were playing piano just a few metres away from the Duke of Edinburgh Building, that building that was struck by lightning around 2:15 PM. And I think we were probably one of the closest people to the strike, maybe about 10 metres away. So a friend of mine suggested that it might have something to do with a talk I gave in this room just a couple of weeks ago about atheism. The Almighty was perhaps sending me a warning shot. But I don't pretend that God has too much interest in me. I don't pretend he exists at all. Right, so there we go. That's the point of the talk. Another friend had an alternative theory. Although we all saw the lightning strike the tower, the damage is inconsistent with a lightning strike. It was actually a controlled explosion with part of a government conspiracy. It was when he told me that the plan was to convince us to declare war on the sky to steal its oil that I knew he was just joking. So given these two explanations, I hope you'll agree are insufficient. What I'm going to attempt over the next short while is to give you a brief description of the damage done to the Duke of Edinburgh Building and around the school. Then I'll attempt a description of what happened during a lightning strike in general, and to do that I'll talk to you a little bit about the history of how we got to our latest ideas. Lastly, we'll go back to the Duke of Edinburgh Building, have a look at it again, and see if we can describe exactly what happened during the strike. So that's the idea. So generally about the whole school, the fire alarms in the school are all linked together by a network, and the idea is that if the alarm goes off in one building, then it sets all the other alarms off as well, just in case the fire moves from building to building, so it's a safety precaution. However, during the lightning strike, a lot of those network cards that communicate the signal were damaged and were not working. They're still not working, in fact. So an alarm that goes off in one building still works, but they're just not connected together anymore. That's why we had a fire drill this morning, if you were around, to check that the new method of manually switching them on works, and it seems to work, so everyone's safe. Part of the internal telephone network, also called the telephone exchange, was damaged. Speaking to the bursar, he told me that 3 of the digital circuits that sort out the communication so you can call one phone from another and it all works out without you having to worry too much about it. 3 of those were damaged and they stopped working, and therefore the communication for the internal network couldn't work anymore. Specifically to the Duke of Edinburgh Building, you see the damage to the roof. I'll show you more of that later. Damage to the telephone, so you see license error endpoint. That's some error message that I'm sure part of the IT department will understand, but it doesn't mean much to me. It means the phone doesn't work. You pick up the phone, it doesn't work, right? There's a closer image of the building. Notice how this has all been pulled off. Many of the tiles flew onto the floor and were cracked, and I've been told by some of the porters that a couple of the beams have been cracked too. Immediately after it happened, as I said, Mike and I were really near it, so I immediately ran out to go and have a look, and I took a bit. I liberated a piece in the name of physics. There it is, and it smells of burned material, it smells of burned wood, and you can have a look at it later if you like. So that's what happened. Going into the building, looking at all the lights on the first floor in the Duke of Edinburgh Building, there are these components called capacitors. I'm going to show you one of them in a minute, and they'd all exploded. When people took the plastic casing off the lights, it was apparent that's what they looked like. I just took a photo of it while it was on the ceiling. Also, the network sockets were damaged. That's the network socket in the little office on the first floor, and you see the damage These are copper wires here, you see the damage to the socket. And the energy must have travelled all the way up the wire, because you see on the other end of the network port that's also black and damaged there too. So that's what happened when lightning struck the Duke of Edinburgh Building. I'm sure that many of you have a lot more information about it, and it would be good to hear those questions afterwards, those comments. All I managed to find out was from snooping around the past few days asking people questions, so you might know a bit more than me. So now back to lightning as a principle. Generally, lightning strikes. There are around 400,000 lightning storms every day on the Earth. There are around 100 lightning strikes hitting the Earth every second. The typical energy transfer of each strike is about 1 billion joules. Now, to get an idea of a joule, here's my bottle of water. That's about a joule, the energy required to lift the water from there to there. So the energy released in a lightning strike is 1 billion joules, 1 with 9 zeros on the end. This is equivalent to keeping a 100-watt light bulb on for a few weeks continuously. It's the energy transfer of an explosion of 200 kilograms of TNT. So a large quantity of energy. To try and understand what's going on, the natural question to ask, especially when it's happened so close to you, is what was that? Now, the first idea about lightning was that it was a godly weapon used to exact punishment upon wrongdoers. I'm sure you've seen the cartoons of people, gods throwing lightning bolts. If you know a little bit about physics, you'll know that this theory has now since been modified. Right? The first suggestion that the idea might need changing was when we figured out how to make taller and taller buildings. It was noticed that the taller, more conductive buildings were hit by lightning more frequently. So we had two options. Either the gods really must hate tall, conductive buildings, or we got the idea wrong. It turns out that we got the idea wrong, and the consensus was soon reached. Partly due to scientific investigation, but also because in most towns and cities, the tallest buildings that often caught fire from lightning strikes were churches, or their equivalent. The motivation to find a better explanation then is partly due to trying to prevent harm to either the things in our lives or ourselves. We've inherited a lot of understanding from our ancestors on this topic, so when we ask the question, what was that, we have a pretty good answer so far. I say so far because there's a lot about a lightning strike that we still don't understand. And more than that, there's probably a lot more that we don't even know we don't understand yet, and that's still yet to come. So this is an investigation that's carrying on still. One of the big steps to understanding it is to remove the idea of a lightning bolt and to think of it as a thing, an object. This is a common mistake that people make, and the idea is useful in physics to think of objects, to think of what you experience not just as objects but also as processes. For example, the ancient Greek and Buddhist philosophers thought the same of a river. If you look at a river, it's not a fixed object, it's a flow of lots of water particles. And similarly, I'm going to use that as a metaphor to describe this. The Greeks, and especially the Buddhist philosophers, also thought that this applies to each of you. What you call me, or I, is to think of yourself as an object when it seems, on careful study, that you are actually a process as well. So it's good not to think about lightning as a bolt, as a thing. I'm about to describe the process to you. Before I start, let me say I'm not going to offer an explanation, not in terms of forces. I think that'll be a little too hard. What I'm going to do is give you a description of what happens. And to do this, there are two ideas in physics that can help us keep track of what's going on. The first one is, where's all the material going, where's all the stuff going, the matter? And for our purposes, that's going to be electrons. And the second is, where is the energy going? So we have a principle called the conservation of energy in physics, which is that there's this number that we add up that always adds up to the same number no matter what changes inside a box that we look at, assuming we don't let anything go in or outside the box. So energy is a number we give depending on two things. Depends on what the things are doing and where they are. The first type of energy that depends on what they're doing is called kinetic energy. An object that's moving faster has more kinetic energy. The other type depends on where objects are, and that's called potential energy. That's a very difficult thing to understand, harder to appreciate, because two objects can be totally still and yet still have potential energy. I did have some little bar magnets, now here they are. So this illustrates. I'm sure you've seen barred magnets before, but you also know that if you've got opposite poles attracting, you have to hold them there with your hands for them to stay there. If you let go, they pull together. It's more obvious when you see it on a table. I have to hold it up like this. So just keeping them close together demonstrates that there's an energy that, say you clamp this one down really hard, this one will have a potential energy, because if you were to let it go, it would pull towards the other one. That's what potential energy means. It's just the energy that something has due to where it is, and then in other circumstances that energy can be released into kinetic energy. So those are the two different ideas. So we're going to look at lightning clouds. There's my diagram, and it's not to scale. A typical cumulonimbus lightning storm cloud is 1 kilometre from the ground to the bottom of the cloud. It's about 5 kilometres wide and about 10 kilometres high. Now, in order to understand the description, you have to know that everything's made of atoms, and an atom is a mix of positive and negative charge. Positive in the middle turns out to be very small, and negative around the outside. And what happens in the cloud is that the water and the ice crystals, because the cloud is very high up, low pressure air, and so you can have ice up there. When there's a strong wind, they rub together, and you can actually get a separation of charge. So you can get, on some pieces of the rain and the ice, you can get some more electrons than normal, and on others you can get fewer. And this is from rubbing things together. I'm sure you've done the same when you've rubbed your head against a balloon or taken a jumper off. You can feel the charges then. So you get negative charge on the bottom of the cloud and positive charge on the top. So all the stuff up here has had some electrons taken off their atoms, and all the stuff down here has had extra electrons. So that's how it works. Now, what this does to the ground is the following. So the ground is normally neutral. It has atoms with positive charge in the middle, negative charge around the outside. But because these negative charges are up here, they repel the electrons in the atoms down here. So what would normally be a positive charge with a negative charge that's symmetrical all the way around, you get an asymmetry, and you get more negative charge towards this end of the atom than towards the top end of the atom. Now, you can think of that as there just being a whole bunch of positive charge on the top and a whole bunch of negative charge on the bottom. That's assuming that the Earth is an insulator, which it mostly is. But when you come to look at buildings and other things like that that are made of metals, then you're looking at conductors, and the electrons can actually move through the material. So here, we're just talking about them being pushed away a little bit for each individual atom, but they're still in the atoms, right? They're just skewed to one side. So we've got this situation now that forms during a lightning cloud. You might ask, where does the energy come from for all of this? Well, it comes from the kinetic energy of all the whirling around of the bits and pieces. Where does that come from? Well, that comes from the heating of air, which causes the wind. Where does that come from? That comes from the sun. Where does that come from? Well, that's a nuclear process, and then you go all the way back to the origin of the universe. So it all flows through from the sun to cause this sort of situation. I'm going to remove the two bits that we're not going to worry about now, which are going to be those two, and we're just left with the negative charge at the top of the cloud and the positive charge at the bottom of the cloud. What happens at this stage depends on how much negative charge accumulates on here. If you get more and more negative charge on here, this negative charge repels the electrons down here more and more, so that they get skewed even further, and you get more positive charge at the bottom. If that happens enough, then we get a lightning strike. And I'll briefly explain what happens. So we've got all these electrons bouncing around here, associated with atoms, and they could, if they had enough energy, they could push the oxygen and the nitrogen atoms here, and they could push away one of the electrons from those atoms. And it's the condition of a lightning strike that you need to have enough charge on either side so that there's enough energy for these electrons to do that, to knock off an electron from, say, an oxygen or a nitrogen molecule down here. How much energy does it take to do that? That process is called ionization, by the way. It takes about 1 millionth of a joule for an electron to get enough energy to ionize an oxygen or a nitrogen atom. Now, you also would need to know how far apart the molecules in the air are to figure out how much energy you need in total. So the distance between typical oxygen and nitrogen atoms in the air, and including in this air, is about 1/millionth of a meter. Yeah? Just to give you an idea of the scale, the distance between two molecules, which is 1/millionth of a meter compared to 1 meter, is the same step in scale as the difference between 1 meter and the distance from here to Marseille in France. Right? So that's 1,000,000 meters. That's the equivalent step in scale you'd have to take to imagine how small these things are and how close they are together. So it does take 1 millionth of a joule for that to happen, and we can rewrite that in a different unit. And the way you can rewrite it, my A-level students do this, they measure it in electron volts, which is a measure of energy. And it makes the whole business easier to understand. It's 10 electron volts for that to occur, for the energy to be enough. So you need 10 electron volts for 1/millionth of a meter. You could then figure out how many volts you'd need for every meter to allow a lightning strike to occur. It turns out you need 300 million volts per meter. So if you work from the idea that you need 3 for 1/millionth of a meter, you need 300 million. You can work it up from, 10 for 1/millionth of a meter, you can work up from there. So if you do a rough calculation, you get about 300 million volts per meter. Now the cloud is 1 billion meters from there to there. So the difference in potential from there to there has to be about 3 billion volts, 3 with 9 zeros on the end. Now that's all quite difficult to understand really, but if I'm talking about volts and things like that, they're difficult concepts. Just think of it like this, that there needs to be enough charge here and here for the attractive nature of the positive charge to pull down the electrons from there, so that they get enough speed to whack into the nitrogen and the oxygen molecules, so that they knock out other electrons, and then they get pulled down more, and they can knock out more electrons from other hydrogen and oxygen molecules. And that process keeps on going. Now that's called a step leader. That's not what you commonly see when you see a lightning strike. So the step leader moves at about 160,000 meters per second, and it takes about 100 amps. That's the current, if you understand about currents, 100 amps going down. While that's going on, these electrons are coming down here and they're ionizing all the air. While that's going on, this gets very, very highly positively charged, and it influences the air around it down here. It can actually pull electrons off the air down here and pull them down there. And what you get is a sort of reverse process. It's called a positive streamer. And a positive streamer comes up here, and it's just air that's been positively charged. It's been ionized by all of this stuff down here. The electrons move down, and you get more and more of a positive column. That will increase when these electrons get closer, because the closer the positive and the negative charges are to each other, the bigger the forces between them. So they pull more and more and more. So you get the positive streamer coming up, the step leader going down. They join together eventually. And you might get loads of different positive streamers. I'll show you a video of one in a minute and a few photographs. When they connect together, the result is a heavily ionized column of air. Now that is called electrical breakdown. And now suddenly you have a column that is electrically conductive. All of this is an insulator, so electrons can't easily move down through it, except for that one column that has the step leader and the positive streamer. That does just work like a wire. Now that's called electrical breakdown. I want to show you a demonstration of electrical breakdown that Mr. Tober's very kindly helped me set up. And I'll just turn the lights back on to do that. What we have here is a capacitor, which is just 2 metal plates, just little bits of foil, rolled up with an insulator in between, normally a piece of paper or something like that. So it's got 2 conducting bits, and you can charge them up with an electrical circuit. So whereas here, this gets charged up with the wind and so on, you can charge up the 2 sides using an electrical circuit. So that's where the energy comes from for that. And normally paper is an insulator, right? It doesn't allow electrons to move through very easily. But if you make a potential difference big enough, 300 million volts per meter for the air, it's different for paper. then you can get it to break down, and the electrons can push their way through just like they do for the sky through the capacitor. I'm now going to connect them up, so I think I just turn it on, is that right?
Yeah.
Andreas? Yeah, okay. And you'll see what happens. Oh, not much. Maybe it didn't work. What do you think? I think about 10 seconds last time. Go on, Mr. Tober, be brave.
Is that on? Yes, yes, yes. Oh.
Uh-oh.
Maybe the storm knocked out the electric, no?
It's like a firework. You should never go back to it, right? Did it? Have you got a different
one?
Have you got a different voltage? Different rating? Maybe we already did that one. I don't know.
Yeah, hot.
Is it hot?
Yeah.
Oh, okay.
Cool.
Don't burn yourself.
That would be good to catch, wouldn't it?
Is it? That's off, right? Okay.
Negative to.
Other way around.
No, the other way.
Other way around. Okay. Right. Let's give it a go.
Get up on the table.
All right. Second attempt. Uh-oh.
I'm sorry.
That's all right. Do you think one of the leads doesn't work?
Let's see. As I said, it's getting hot, so...
It is getting hot. We'll leave it going. Maybe it'll explode in a minute. It'll be a nice bit of suspense for you, yeah. Especially for the first row. All right, well, I'll turn the lights back off. You get the idea. We'll see if that explodes. So that's called electrical breakdown. When that occurs, that leaves a column that allows conduction to occur, and we've got loads of electrons here as well as these positive ions, and they can now freely move down to the Earth, and they do. They start from the bottom, so the electrons nearest the bottom move down, and then the stuff higher up moves down, and so on and so on and so on. And that's called the return stroke. That's the bit you certainly do see, and that's when most of the energy is released. It travels at about 1/10 the speed of light, because instead of having all this problem of having a whack into all these oxygen atoms, it's now got a clear path straight through, and the energy transfer occurs at about 1/10 the speed of light. What you see as light is the energy released when electrons then recombine with atoms, and that gives out energy. So when they do that, you see the lightning flash, and the thunder is due to the fact. Oh, there we go.
Whoa!
The thunder
Wow,
is
that was impressive.
like that.
Yeah.
Good, good.
Do it again.
It was as scary as that bolt of lightning.
Not quite as scary. We're a bit closer this time. The thunder is due to the air being compressed and heated so much, it's heated more than the surface of the sun, and this pressure causes the loud thunder that you hear. It's two different aspects of the same process. So here's an animation of what I just described. This is from Wikipedia, so I encourage you to look at it too. We have, I think I click, oh no, too far. I'll come back to that. Let me click here. So here you have the step leader coming down, pushing its way through, knocking out electrons and taking others with it. Meanwhile, these positive streamers are coming up from objects, and when they connect together, you then have a conductive path for the energy to move through. To show you that these positive streamers do come up from many different objects at once, here's a really amazing photograph of the brightest patch is the return stroke that you see, so that's where most of the energy transfers occurred. So the step leader and the positive streamer have combined somewhere, it's hard to say where. But look, there's another positive streamer there coming off this tree, and there's another one here coming off what looks like a street light. I'm not quite sure what that is. But you notice it's actually attracted towards the step leader, this main step leader here, because there'd be loads of electrons in here. So that's the direction that the ionization occurs in. There can be many, many return strokes in one lightning strike that you might not be aware of. You see the whole thing is just one flash. Sometimes you can see a flicker, but mostly it seems to be one lightning strike that actually is a process for a large number of different things. Are you going to turn the power supply?
Yeah.
I think that's a good idea. Thanks. So there's a closer image of the positive streamers coming off the tree and the and the light there. Here is a video I want to show you. I hope Tom Warner doesn't mind. I didn't have enough time to ask him, so it's copyright Tom Warner. And this is a high frame rate image of a lightning strike. You see the step leaders coming down, and there's the return stroke. And there'll be several of these over this short video that I want to show you. What I should say now is that this is taken at 7,200 frames per second, and it's been slowed to just 60 frames per second. Look at the bottom right of the video, that's a truck. And that truck is on a road moving at 60 miles an hour. But you didn't see it move during the video very much at all, I'm sure. And as this continues, I think this is the last strike you'll see. You'll see in a moment the windscreen wiper of the car that this is filmed from, I hope, if we get to the end. You can see it. Making us wait for it. Oh well, trust me, you go find it out. Tom Warner, you can go see the video yourself. Alright, so back to our predicament, what happened to the building. It presently isn't feasible to control all of this stuff, the lightning strikes. So the best we can do is protect buildings to reduce the chances of damage to its structure, its contents, and the people inside it. One way to do this, discovered by Benjamin Franklin in the late 1700s. This shows you how underprepared I am. I haven't even got a picture of Benjamin Franklin. I should be ashamed of myself. So he discovered in the late 1700s that if you attach a conducting metal rod to the top of a tall building, and you connect it all the way down and then stuff it into the ground, then you significantly reduce the damage to a building from lightning strikes. Initially he got it wrong. He thought that it would reduce the number of times the building got struck by lightning. It actually increases the amount of times the building gets struck by lightning, but reduces the effect significantly. This is the one near the science building, and if you are unfortunate enough to be one of my Year 8 students, I might have dragged you out to go and look at it. So next time you're there, have a look. It's running, this is the lower school playground there.
It's that strip here, the
Oh yeah, thank you.
coppery green strip.
Oh yeah. I should have pointed that out, thank you. We took the photo, you see, Mr. Tober and I, so he wants to make sure that you know where it is. That's a good point. So that's one way of doing it. Now, why does that work? Well, it works because when the step leader comes down and these positive streamers come up, the most effective positive streamer will be the one that's going through a conductor where the electrons can move freely and they don't need to be pushed down through electrostatic attraction. So when the step leader comes down from above, all the electrons in here are going to be repelled very easily and they'll move quite simply through this conducting metal down. And that allows the positive streamer to form from the tip of the lightning rod. So when lightning strikes a lightning rod, it's because it's been designed specifically for that purpose. It's asking for it pretty much. It's sending the positive streamer up to meet it. And that's how it's designed. Now if you look at the Duke of Edinburgh Building, where we had our strike, there aren't any. I looked all the way around the perimeter, there aren't any conducting rods on there at all. Now you wouldn't think you'd need one, because the building is a lot smaller, lower down than the other ones, and there are conducting rods on the higher buildings. Interestingly, if you go down here, I've been down here, there's a lot of very good graffiti down there. You should have a look. People carving their names in from 1903 and things like that. You should check that out. I managed to get up into the roof of the Duke of Edinburgh Building and had a look inside. They cut a hole out during after the strike to see what the damage was, and I didn't quite brave it in there. The reason is that these are the only beams for the roof. All of this stuff here is for the fake ceiling. That's just, you know, people put wires above fake ceilings now, and this is an example of one. These metal wires here then are to support this fake ceiling. And many people have been asking me why there hasn't been any damage to the weather vane on the top of the Duke of Edinburgh Building. The reason for that is probably that a positive streamer came up through this metal material, and this metal material here, this is where the clock tower, well, it's not a clock tower, it's just a tower. This is where the tower is, so above there is the damage, somewhere in there. And right next to it are these metal struts. So I'm guessing, I don't know, but my best guess is that that's a very good conductive route for a positive streamer to come up through the ground, through the building, and connect with the step leader. And that's why the building was hit there. If there was a conducting rod from there down to the ground, then the building, the roof, wouldn't have blown apart. All the energy would have been directed down the rod. So instead of that, I think the energy went down through here. There are a lot of wires associated with the lighting down here, which probably exploded the capacitors because the energy went through the lighting, and then found its way through the telephone and the fire alarm system and caused the damage down through there. So this could have been solved perhaps with a little bit of copper wire running from the top of the building down to the bottom, and I think that's as much snooping around as I've managed to do. The building itself, the tile damage here, could have been caused by, Mr. Tober has been speaking to me about this, there being a felt lining underneath there, and the reason that trees often explode when lightning strikes them is that the energy from the electrons heats up the water very quickly, and the water expands and then actually breaks the rest of the material, so trees explode that way. And felt, if it got a little bit wet, then would have experienced this superheated water and exploded the tiles off the roof. So presumably that's what happened. Thanks for coming and for listening. If anybody has anything to add, that would be really interesting, I'm sure. But otherwise, you're free to leave. Thanks. Thanks.